Okay, so it's my great honor to introduce today's speaker, Professor Joe Subtonic. Joe got his PhD in electron structure theory from UC Berkeley in 2006 with Barney and Gordon. Then he moved to Israel, Tel Aviv, to study dynamics as a postdoc under Ab-Initio from 2007 to 2009. Ab-Initio. Okay. From 2009 to 2010, Joe was a postdoc fellow at Northwestern University under Mark Ratner. Joe then joined the chemistry department at the University of Pennsylvania as an assistant professor, and earlier this year he became an associate professor. Joe's research is focused on intersection between electron structure and chemical dynamics, with special interest in condensed phase photophysics and photochemistry. So next he's going to give a talk. While he's talking, please send in your questions. Joe.
Okay, so hello everyone. This is my first time ever giving a webinar, so I apologize if I sound a little bit confused or awkward. Speaking into the abyss is not so simple. Please, if you have questions, make sure you email Yihan. Yihan is right next to me here, so I'll be able to hear them and perhaps even see them in real time. Let me also thank Zheng Ting and Yihan for setting this whole thing up. They are the backbone of Q-Chem, and I'm really indebted to them. A lot of my research has involved Q-Chem. It relied on it very heavily. A lot of my research has involved Q-Chem and relied on it very heavily, and I'm very happy to be here. Okay, I've got one caveat about the talk I'm going to give you. I'm going to tell you some things about the research that we've done in electronic structure theory. So my audience is going to be intended to people who are used to using Q-Chem to solve problems of quantum chemistry. They're interested in real molecules. This will be almost entirely a quantum chemistry talk, not a dynamics talk. That's the other half of my research, which is very interesting, but it probably would be best saved for a separate webinar if we were going to show that as well. A second caveat is that, as I say below here, the references I'm going to give you are unfortunately not going to be complete. There's a long history here in the field, and so I'm going to give you a little bit of history, but I'm not going to give you the full history. I'll be highlighting what we've done and what's actually available in Q-Chem. Okay, and this was all funded basically by the National Science Foundation. So here's an introduction. Here's an outline of what I'm going to talk to you about today. So I want to tell you a little bit first about phenomenology. What is electronic relaxation, particular energy or electron transfer? After going through some of the experiments that we've studied in great detail over the last few years, I'm going to dig into the two main parts of the talk today. One is if I want to understand electronic relaxation and energy transfer from the perspective of quantum chemistry, the first thing I can do is I can try to look at the derivative couplings, and I'll give you a good deal of background about how to understand them, what they mean, and then I'll look at some applications. And then, time permitting, I will give you a second view of electronic structure theory, which is a very different one than many of us have taken before in the world of quantum chemistry, but a very useful one also, which also has its role to play. And here I'll talk about diabatic states, and I'll conclude thereafter. Okay, just an overview of some of the experiments that are so interesting here. Your typical experiment in photochemistry is that you come in with light, you wait, you excite, your light has energy on the order of several electron volts. It excites some electrons, and then later on you wait to see what happens. What happens to that energy? Does it eventually lead to charge separation? Is that where the energy goes? So it goes into the Coulombic attraction of being broken of a positive and negative charge. Does it go into vibrations in the end? Does it go into light? All of these are possibilities. So the experiments that we were focused on first, and that are probably the essence of the most well-studied and famous energy transfer experiments, are the CLOS electronic station transfer experiments. So the physics that you have here is you have an system in its ground state, excited by, I think it's 3 or 4 electron volts, going up to a singlet. Then it transfers over to a triplet by Al-Sayed's rule on the molecule here, which we've drawn as benzaldehyde, but really it was benzophenone in the experiment. And then by measuring the T1, T2 signature of either the benzaldehyde or of the naphthalene, you can actually tell how long it takes for the excitation to move from the right to the left. And okay, so what do you find experimentally? So again, these are triplet energy transfers. So on the right, you have to 0th order approximation. You have an n to pi star states. You have an n orbital here being half empty, and a pi star orbital here being half full. And this is going to transfer. This electron is going to go. The electron on the right here went over to the left, and the electron on the left here went over to the right. So people often think about triplet energy transfer as a 2-electron process. And then the question becomes, how do you model this with quantum chemistry? Before we start modeling it, let's just sort of go through why these experiments were so interesting. They were so interesting and why they were been cited over 1,000 times each of them, because they showed something very interesting about the distance dependence of energy transfer. In this case here, I'm showing you 11 molecules in front of you. The A stands for naphthalene, and the A stands for naphthalene, and the D stands for benzaldehyde in our situation. They really had benzophenone in their experiments. And what you see here is that the C's here stand for cyclohexane, and the D stands for dicyclohexane. And in this molecule here, what you find is you have 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5. This one actually, these are actually mislabeled. No, it's not mislabeled. This has 6 bonds in between donor and acceptor, and this has 7 bonds in between the donor and acceptor. And as a function of the donor distance, you can actually see how long does it take for the excitation to actually move from side to side. Waiting for the delay here. Yeah. So what you find is that if you have 4, 5, 6, or 7 bonds, the rate goes exponentially with the distance in between. This is the original data from that paper in 1988. So the logarithm of the energy transfer rate is proportional to the number of bonds in between. In other words, the rate of transfer is exponentially inverse proportional to the number of bonds in between. And the slope here is about 2.6. It's a factor of 2.6 times slower every time you add on another carbon-carbon bond. There's something also very interesting about these experiments that was shown you was if you consider if you consider what happens in a similar experiment where you actually take that same set of molecules and you add on another electron, and now you watch an electron move from donor to acceptor, what you find is that the distance dependence there is such that if there's a decay for energy transfer is measured by alpha, and the decay for electron transfer is measured by beta, there's a fundamental rule that tells you that alpha is about 2 beta, which means effectively that the energy transfer rate falls off with distance twice as fast as the electron transfer rate. All of this is the phenomenology that we see. It's very interesting in principle, and we were very interested in the beginning about exploring these questions with theoretical chemistry, and Q-Chem was our platform of choice because as a developer, I knew exactly what was inside Q-Chem, and I knew that it would be very straightforward to put all this functionality into Q-Chem. And so let me now tell you what we've actually done. Okay, so the first part of the talk, derivative couplings and their meaning. How are we going to model the situations that we talked about above? And I'm going to give you what I just discussed for you. So the question is, I want to model this electron or energy transfer process, right? Is quantum chemistry useful? How can Q-Chem help me, right? So before we actually talk about that, let's just go back to basics for a second. Forget about electron and energy transfer for a second. Just think about your undergraduate chemistry. What we learn about in quantum chemistry is that the whole difficulty, but also richness of quantum mechanics comes from the fact that the Hamiltonian, which has the kinetic energy and the potential energy, do not commute, right? And the backbone of quantum, of Q-Chem is diagonalizing, or, coming close to diagonalizing a big matrix and solving the Schrödinger equation. But it's important to remember that in general in Q-Chem, that matrix entirely represents an electronic problem. So, in fact, if we think about the most basic code many of us have written in Q-Chem, right? And we're looking at hydrogen and looking at a Hartree-Fock calculation. One thing you notice is that in this calculation, the mass of hydrogen is never even given. We don't specify hydrogen or deuterium. In fact, they're all the same. We have standard, all that matters as far as the electrons are considered, as far as the electrons are concerned, is the electric field that's generated a nucleus of a given charge. And all of the methods that we're used to using from Q-Chem, of course, and any electronic structure package, Hartree-Fock, DFT, CIS, MP2, they're all about solving the electronic Schrodinger equation. They have nothing to do really with any. They have nothing to do with nuclear motion in any way. Now, it's important to remember that for the problems we're talking about here, electron energy transfer, nuclear motion is absolutely paramount. And of course, that shouldn't surprise you. You know that in the situation I just told you about, if an excitation of triple energy is going to move from one side of one big molecule to another side, the energies are not going to exactly match up in general, and some of the excess energy has to be dumped somewhere. Where does it get dumped? It gets dumped into the nuclear vibration. So clearly the nuclei are important. And in fact, if we go back to the Schrodinger equation, the Schrodinger equation always has the kinetic energy of the nuclei, the potential energy of the nuclear repulsion, the kinetic energy of the electrons, the electronic repulsion energy, and the nuclear electronic attraction. If we write all of this together, and we take these last four terms and we group them all just into the so-called electronic Hamiltonian, then of course what we get is that this whole structure here is what we actually are diagonalizing in Q-Chem, or we're trying to diagonalize it. It itself is a very hard problem. The solution just to this part itself would be a full CI problem, and of course we can never really do full CI. We have the best approximations we can get. These are called adiabatic states in the context of what Q-Chem is giving us. Now, we have these adiabatic states, and if we change the nuclear positions, we get potential energy surfaces. So some surfaces might look like this. These surfaces have a ground state, which is here given in red, and an excited state given in blue. And here it looks like the potential energy here is going to be minimized around 1.4 angstroms. Now, we have these potential energy surfaces, but it's important to remember, and to keep remembering, right, that the nuclear kinetic energy does not commute with the electronic Hamiltonian, which is the basis of everything that all that Q-Chem is doing. And because of that, you really still have only solved half the problem once you have the potential energy surfaces. There is still the nuclear problem out there, and this is something that is just important to remember about if you're interested in quantum chemistry and you want to know how to handle electronic relaxation. So what can go wrong? Well, what can go wrong is that not all surfaces will look like this. Some of them will look like lithium fluoride, one of the classic canonical examples of an avoided crossing. In this situation, for lithium fluoride, you know that the ground state, which happens at short distance, has an ionic bond between lithium plus and fluoride minus. However, at long distances, the lithium fluoride will prefer to have lithium plus and fluoride minus. Will prefer to have a neutral lithium plus, lithium and fluoride, and the charge configuration, which is lithium plus and fluoride minus, will be higher in energy because you actually have to separate two things which have opposite charges. There's an attraction there, and you have to break that attraction. So the character of these states changes as you go here. The ground state here is ionic. The ground state out here is more sort of covalent or charge neutral. But up here, the ground state is ionic, and over here, the charge state, the first excited state, is also going to be charge neutral. Let me sort of show this. I want to show this, but before I get into what a derivative coupling is, I just want to sort of say a couple words about how all this relates to a very simple problem in mathematics. Here's a matrix that I want to diagonalize. It's a pretty straightforward matrix to diagonalize, and I can diagonalize it. I can use MATLAB, and no problem. Okay, so what's going to happen? If I can diagonalize this matrix, what if I actually want to diagonalize a set of matrices? So this matrix here, I'm thinking about it as being parameterized by a parameter r, and r equals 4 here. So for instance, you can see here this matrix 17 is 1 plus 4 squared. So if I just plug in one value of r, I get this matrix and I can diagonalize it. And now I can make up a whole bunch of matrices which are all parameterized by one by one external parameter here, which I'm calling r, basically because of course it's going to stand for the nucleus. And if I want to diagonalize this entire set of nuclei, if I want to diagonalize this matrix for any given r, it turns out there's a nice analytical form. It looks like this. It's very simple. You can find the eigenvectors, you can find the eigenvalues, which involve, this is proportional to the eigen. These are proportional to the eigenvectors. Proportional to the eigenvectors are not normalized. These are the eigenvalues. This is a very simple thing to do. We all know how to diagonalize matrices. But of course, where derivative couplings come from is the fact that we can't diagonalize this matrix down here. We can't diagonalize this matrix because although this might seem like it's diagonal, this itself is multiplied by the identity matrix, 1, 0, 0, 1. This is not diagonal over here. And so why can't we diagonalize it? Well, okay, we know how to diagonalize that second matrix over here. we can diagonalize it in this form. And if we diagonalize it like this, we can always put it in the form of U times the eigenvalues times U, matrix of eigenvectors times matrix of eigenvalues times matrix of eigenvectors. So then we would say, what you would say is, okay, to diagonalize this whole Hamiltonian, I would just multiply by U dagger on the left and U on the right. And then I would change basis, and effectively my new Hamiltonian would look like this. What you notice is, in general, the right-hand side now is diagonal, but the left-hand side is now no longer diagonal, right? Now this piece is not diagonal. There is no free lunch here. So so every time, even when I can take one matrix and diagonalize it as even for a given arbitrary parameter R, if the matrix of eigenvectors or eigenvalues depends on R, then what you find is that if you're adding a second derivative operator, the whole Hamiltonian itself can no longer be diagonalized, and that's where things stand. So let me sort of just say two more words about where this comes from in the context of the Born-Oppenheimer approximation and what's going on in quantum chemistry. In general, Q-Chem gives you adiabatic electronic states. What does that mean? Well, it means that in this total Hamiltonian, which is the nuclear kinetic energy, and as the electronic Hamiltonian, we diagonalize this Hamiltonian and we get eigenvalues and eigenvectors. And these eigenvectors then in the Born-Oppenheimer treatment can be used to solve for the total Hamiltonian, for the total wave function, which would be the sum of a nuclear of a nuclear amplitude of a wave of how to put this here one more time here. I want to call this basically I want to call this a coefficient, which depends on nucleus. Nuclear geometry here, times an electronic wave function, so a nuclear wave function times an electronic wave function. And when I plug all of this into the total Schrödinger equation, it's going to look very simple. I have the kinetic energy of the nuclei plus the potential energy, and I want all of this in theory. This should be the electronic Hamiltonian here. I want all this in theory to equal my total energy times my times my total wave function. When I go through the math, unfortunately, what happens is, and I do apologize, this is actually a typo here. No, there's a typo on the previous page. There's no typo here. What's going to happen is that what I'm going to find is that when I do my basis set expansion over my different adiabatic states, I'm going to find that now I get the kinetic energy plus the potential energy on one surface. These things are going to equal the total energy times times my wave function on the same surface, but I'm going to have all these mixed up things in here, which come about from the fact that the nuclear kinetic energy operator operating on the electronic Hamiltonian do not commute. And because of that, I get all these mixed up things here. It's really a mess. The quantum chemistry books you'll see are always a little bit tedious to read through, but it's important to not lose sight of what the physical intuition is. This operator in here is what we're talking about today. It's the derivative coupling operator. What it tells you is how much does the ith electronics wave function depend on nuclear position, and how does that actually overlap with the jth electronic wave function? I'll show you some pictures in a minute. Notice the key thing here. The key thing is that this operator here is being multiplied by this operator here, which looks like the momentum of the wave packet on the ith surface. So what's happening is that this operator is telling you that nuclear density on the ith surface, if it's moving, can actually move to the jth surface. That's simply the basis of what these derivative coupling operators are. They are telling you entirely about electronic relaxation, and I'll show you more about this in a minute. This is basically the end of my slide about introduction here, I believe. Soon I'll be showing you some examples. The key thing to notice now, though, is that although these matrices may look complicated, many people in the literature assume they're small. These are not necessarily small. If you follow the work of David Yarkoni, who's been studying these things for a long time, he's shown just how big these items can be. And actually, at a conical intersection, these matrix elements are huge. So the key point is this, to take home away from it. If we got rid of this term right here, right? If we got rid of this whole term here, which is blown up over here, we would tell the different adiabatic electronic states that we get in quantum chemistry would entirely be uncoupled. So it would be like as if you had the ground state and the first excited state and the second excited state and the third state, and you could just think about doing dynamics on each individual state. It would be just like doing excited state chemistry was the exact same thing as doing ground state chemistry. You would never have to worry about one surface interacting with another surface. Of course, that's not true, right? we all know that eventually, if you shine light on a system and you excite it to some excited state, eventually it actually does return to the ground state, which means that the surfaces are coupled, and all of that information is being hidden in all of these matrices over here. Okay, so, now one simple thing. This matrix, these matrix elements that we're interested in, we should think about them as you have two, as being written like this. You have one electronic wave function, which is going to change with nuclear position, and you want to know how it changes relative to the first electronic wave function. There's a nice formula which I actually derive over here, which I'm not going to go through here, but there's a nice formula that tells you when this matrix element is big. And this is sometimes known, I believe, as the hypervirial theorem. I forget what it's called. The key thing to notice is that these matrix elements are huge when the energy gap between states is small. So let's go back to lithium fluoride. What you find here is that in lithium fluoride, we know that around 7 angstroms or so, there's actually going to be, for the ground state and the first excited state, there's going to be a crossing where this state, which up here we know is actually, the first excited state we know is ionic up here, it's actually going to become covalent over here. So it's changing a lot here, as is the ground state. The ground state is changing from covalent into ionic. These two states are changing dramatically, and that's all exemplified by this derivative coupling, which is telling you how the excited state is changing relative to the ground state, and it's all peaked. It's basically zero everywhere except around 7 angstroms. Okay? So that's the typical thing that we expect to see for a derivative coupling. Now, one more thing that will be useful here. I told you before that you can that in general you should be thinking about this 2x2 matrix as something you diagonalize to get the adiabatic electronic states as a function of energy. The U's here, these are the matrix of eigenvectors of this original matrix, which is like a Hamiltonian. These U's, because they're just 2x2 rotation matrices, you can always write them like this: cosine theta minus sine theta, cosine theta. Theta, if you take the theta dr, that's also the same exact thing as the derivative coupling I want to mention. Okay, so some applications here. What can you actually do with this? One of the big things that we studied before, and this goes now, and this was done. This is an application that was looked into by a student in my group, Chi-U. One of the items that we studied has been benzaldehyde's relaxation by itself. So phenomenologically, what's thought to happen here, what's known is that benzaldehyde is a very strong emitter of phosphorescence. So the physics that you think we understand is that you come into benzaldehyde, you excite, you go up to a singlet surface. Once you're on the singlet surface, you can quickly go into a triplet surface. This is actually according to El-Sayed's rule, which says that n to pi star and pi to pi star transitions are very well coupled, which is true. In this case for benzaldehyde, that's what we have. And then we don't know exactly how it works. Is it a conical intersection? How does it work? We don't exactly know, but there are actually two excited states here. And this state, the question is, does it actually feed into a second state, which then actually converts downhill? That was the picture that we thought should be true. And this is actually the picture that we confirmed to be true in this paper that's now shown here down below. How do you do this type of thing? So I'm not going to show you how you actually convert, how you actually construct the transition rate going from singlet to triplet right now. We can talk about that later if you like. You can ask a question about that. I'm happy to tell you about that. I just want to tell you right now about how you actually model going through this conical intersection. What can you say about it if it even is a conical intersection? So first of all, this is the code that will just give you a general excited state for benzaldehyde. The nuclear geometry of benzaldehyde. The job type is single point. The exchange we used was the Head-Gordon functional omega B97X. We looked for 6 CIS roots. This is all just information about static and total memory, not so very important. We're looking for triplets, and we're also looking for singlets here. Okay, when we ran code like this, what you find is that indeed, as you might have thought, there are actually 4 interesting valence states, 2 n to pi star states, 2 pi to pi star states. The n to pi, and then you have each variety. You can have singlet n to pi star and triplet pi to pi star. What you can notice here is that an n to pi star really should be an electronic state where so what am I plotting here? These are the 4 interesting valence states of benzaldehyde. The n to pi stars, if they were pure n to pi star states, they would actually, well, okay, right, so what am I plotting here? This over here, is going to be the detachment. This will be the detachment density, and this will be the attachment density. And what you're noticing here is that the detachment is not coming entirely from n to pi star state. The detachment is coming entirely from the O, which is up here, but the attachment is not going entirely into the pi ring. It's actually staying partially on the oxygen. So it looks like the n to pi and pi to pi star states are not entirely a clean separation. That being the case, there are 4 states here, and you can then analyze exactly how these states interact and how strong interaction is between the 2 triplet states that we're interested in using quantum chemistry theory. So here's code to actually generate derivative couplings in Q-Chem now. All this has now been added to Q-Chem. If you want to look at this molecule benzaldehyde at a given geometry, it's very simple. All you have to do at the bottom is say CIS dare couple. I want to do one derivative coupling calculation between 2 states. And what states are those? I want to look at the first and second excited states. And if I do that here, what I find is that at this given geometry here, I actually get that the derivative coupling has a pretty big magnitude, 55 atomic units. Typically speaking, anytime you're over 1, you're sort of close to something interesting. And maybe something on the order of 10 to the minus 2 is sort of pretty boring. That's sort of the typical thing you're thinking about. 55 is a very big number. What does it look like? Well, what we did was we actually sampled a whole bunch of different geometries, and then what we find is that the geometries, that the directions of the derivative coupling vectors can take 2 different forms, just depending on what geometry you're looking at. Sometimes they can look like this, where the molecule is going to be squeezed in according to this ring. It's going to be sort of squeezed together, and then one like this where the oxygen is going to be puckered up. These are the 2 different directions you can get for the derivative coupling. And this is all done by my student Chi Wu. So the fact that the derivative coupling actually takes on 2 different directions, but only 2, is actually a pretty good indication that you have a conical intersection here. So indeed, what we showed was by changing the geometry and moving around, just doing a whole bunch of single point energy jobs, we could find that over a surface, necessarily, there was in fact a point in the surface where the 2 adiabatic electronic states had the exact same energy, and if it went around them in the branching plane, they actually lost that degeneracy. But for many directions, the degeneracy was preserved. So you can, if you know what's going on, if you think you have a conical intersection, the first thing you can do is you can just go and run some single point calculations and see if it actually looks like it. Do you actually get the right behavior for what the conical intersection should look like? The true test of a conical intersection is actually then, once you actually find that the derivative couplings always lie in one plane, is to actually make a loop in that plane. And when you make a loop in that plane, if you can show that the derivative couplings always point in one circle around it, and they have a given phase, that's Berry's phase, and that actually confirms the conical intersection. Okay, so the story here is that indeed there is a conical intersection in benzaldehyde. The next question you're going to no doubt ask, of course, is, so you know there's a conical intersection, what do you actually do with it, right? So before I try to answer that question, let me jump to the other example I want to tell you about, which is back to the Claus system. So the Claus system, again, up here, for a given set of bridges, we have a donor over here, which is going to be the donor is over here, which is going to be benzaldehyde, and the acceptor is over here. It's going to be naphthalene. What you can do with Q-Chem very simply is you can actually do a set of optimizations where you optimize the geometry of the system to give you the optimized geometry in the T1 state, in the first triplet state, or but in fact you can find two. But if you run a couple of but in fact what you can do, if you just start with two different geometries, you can actually find two different geometries in the T1 state, and then you can just walk between those two geometries. And at every point walking between the two of them, you can just plot the T1 and the T2 energies. And if you do that, what you find is this nice curve here, where it looks as though there's what looks to be a crossing. That in fact the energy of the lowest state changes abruptly at some point along the interpolation. Okay, what is the red curve here showing you? The red curve here, if you take its derivative, okay, so what is the red curve? The red curve is the theta angle that I told you about, which is how you actually define the eigenvectors of the adiabatic matrix, and the derivative the derivative of this red curve would actually be the derivative coupling. So the derivative coupling here would be enormous. In fact, how big is the derivative coupling? This was done by my old student, my old postdoc, who's now in Utah, Shervin Fatihi. He actually computed the derivative coupling at that point here, where the two surfaces came together, and he got an enormous number, right? 2,840 atomic units. The derivative coupling is in units of 1 over Bohr. Okay, it's a 1 over length description. But I promise you that is an enormous coupling. Of course, to really interpret it correctly, you'd have to put it in. You probably want to think of it as an energy or a time scale. Well, we'll come to that in a little bit. Okay, so how do you actually? So this is just showing you what the output is for this type of a molecule. You're here. You see what the derivative couplings are. One thing you can sort of learn if you think about. It's very hard to have intuition for what these derivative couplings will look like. It's not as though, in my experience, somebody can say, I did a calculation, I found the derivative coupling, and now I know these are important motions that I should have known would be important. The derivative couplings really tell you when the adiabatic approximation breaks down and when two surfaces are coupled. It tells you which motions of nuclear geometry break the adiabatic approximation. It does not tell you something obvious about energy relaxation. That's not in there. It's really a dynamical effect, which is very hard to interpret. I can't look at this picture and tell you why these are the important motions that appear in this derivative coupling. So you're at a loss right now. Maybe you're saying, boy, this talk is pretty terrible. After all, you're telling me that every time I do a calculation in Q-Chem, I should be, if I do an excited state calculation, I should be looking at the derivative couplings and to tell me basically whether my surfaces are mixing at all and whether or not something is missing from my excited state calculations. If the derivative couplings are 0, I know I'm good. I know I can interpret my calculations as easily as I want to. I can just think about having a ground state and isolated excited states. But if I have big derivative couplings, what do I actually do? All I know is that things are actually not working and that my naive picture about isolated excited states is wrong. Then it seems like I have to basically do something else, and that's right. If you want to get a rate of relaxation, it is not enough just to calculate a derivative coupling. You have to do more than that. You have to really run nuclear dynamics. Now, there are many approaches to doing this. In my group, we've actually invested quite heavily in the surface hopping methodology, which is one thing I'll just tell you 2 slides about right now. So surface hopping works as follows. And surface hopping is certainly available in what's known as a branch of Q-Chem right now. I imagine it'll be available in the next trunk. Johan's here, assuming that it's in May. So in May. Okay, so very within 6 to 8 months, this should be available, and maybe sooner, depending on need and demand. So how does it work? Surface hopping works as follows. You ask a very simple question. Let's go back to the simplest item we had before, lithium fluoride. Imagine starting lithium fluoride, and we have lithium plus and fluoride minus all starting at the molecule starting at 5 angstroms. Okay, now this is this molecule is not in equilibrium by any stretch of the imagination, right? What we know is that this molecule, if we were to let it go, the lithium plus and the fluoride minus would be attracted to each other, and it would want to get closer and closer and closer to each other. But then you ask a question, right? If we actually let the molecule, if somehow we could freeze the molecule, the nuclei and the electrons, and then let them go, we also know that you wouldn't form lithium fluoride, the bond, every time. There's some probability to form a bond down here, an ionic bond, but there's also some probability that you would actually have the 2 items come together and then actually reflect and go right back out. All of those things are possible. They all will happen with some probability. So what surface hopping says is that instead of running one calculation, in the same way that when we run molecular dynamics simulations, we always have to sample over a big enough pool of initial trajectories to get thermal statistics. I'm not sure what's going on here. Let's hope that that's good. I hope everybody can hear me. If they're not, maybe they would be emailing you, right? Okay. What will happen is we'll run not just one trajectory, we'll run 4 trajectories. And with these 4 trajectories, we're going to run them, and some of them are going to run on one surface, and some of them are going to run to the other surface. And the whole idea is that the probability of hopping between surfaces is actually proportional to the d, to the derivative coupling that you actually just calculated. So understanding the derivative coupling, if you actually know the velocity that your molecule is moving at, that's actually enough. Basically, if I think about the derivative coupling, it's in units of 1 over meters, times the velocity, being meters over seconds, that's going to give you effectively, to 0th order approximation, just the rate of hopping between surfaces. Again, 0th order approximation, with some other strings attached. So that's why we care about the derivative coupling, and that's what we can do with it. And that's now, this type of surface hopping approach is available in Q-Chem now, and I'm happy to answer questions about that as well in the question and answer period. Okay, let me just show you what you can do for the molecule then that I was telling you about before, the Claus system. This is going to be work done by Brian Landry, which we ran for quite a little while. And the idea is that we're now going to look at this molecule. We're going to simulate what happens with the excitation first being on the donor, which is over here, the benzaldehyde. And the excitation, you're not going to be able to see it. What you're going to notice is that when the excitation moves all of a sudden over to here, the molecule is going to rotate. And you should be able to tell necessarily that something interesting has happened. And what's happened is that excitation has actually moved. Now, the time scale for this to happen experimentally was 20 femtoseconds. I'm going to show you now about 1 femtosecond. We ran 100 trajectories like this, and this was the only one that actually reacted within 1 femtosecond. You'll see the total results in a minute. What you're going to notice at around 800, at about 800 attoseconds, so 0.8. I'm sorry. No. At around 800 femtoseconds. Okay. So I'm going to show you a picosecond. Right. I'm going to show you 1 picosecond, and only 1 trajectory reacted in a picosecond, and that trajectory had the energy transfer happen at around 800 femtoseconds. And what you're going to notice at 800 femtoseconds is that you're going to see a big blue arrow that signals the derivative coupling. That derivative coupling is the directionality that breaks the Born-Oppenheimer approximation. Now, for these types of molecules, if we just go back for 1 second to here, we're trying to sort of go up to a barrier and then come back down. If the derivative coupling were big enough, we might actually hop up onto here. But because we're going to look at one that goes right over 800 femtoseconds, we're going to look at a molecule that actually goes back down like this. So here's what we got. Here's a trajectory. Is that running? Okay, here it's running. Okay, everything's hunky-dory. 300, 400. All of a sudden, at 800 femtoseconds, we're going to slow down. That's the direction of the derivative coupling. The derivative coupling is absolutely huge. We're right near something interesting here. And then after that, we pass through. We actually do not hop. The molecule bends. And now that it's once it's turned, what you can tell is that over here, though I can't show you in density, it would take too much memory up from the machine. The excitation is actually now localized over here instead of over here. So what do we get for the statistics of all of this? Well, I don't have time to exactly tell you what AFSSH means, but FSSH stands for fewest switches surface hopping. It's John Tully's version of surface hopping. And if you use the standard version of surface hopping or our version of surface hopping, you're very close to the right answer here. About 20 picoseconds is the experimental time. We predict 15 or 10 picoseconds. So really, you can produce all of this data with Q-Chem in a very reliable way now, and it's basically all been automated for you. So up here, we're plotting on the left hand, we're plotting the population of the excitation on the benzaldehyde. It starts at 1, eventually it will go down to 0 because there's about 0.8 eV energy difference in the between having the excitation on the donor or on the acceptor. Okay, one last thing here, which is really fun, is that what you can do with the code that's in Q-Chem and available for derivative couplings, what you can actually look at is you can actually plot the derivative couplings around. You can pick a point where the derivative coupling in your longer trajectory when you run a surface hopping calculation is huge. And then you can actually take a whole bunch of points around that one point that you isolate. And when you look at that point, you can actually look in a circle around that point. You can actually plot the derivative couplings. And here what you're saying is that In these two coordinates, which I'm not actually going to define for you, we made a little circle, and we were actually able to show that the derivative coupling again went in a loop, which was proof that this molecule actually went right through a conical intersection. So, conical intersections are very interesting items for funneling energy very quickly through excited states. What you're noticing here is that you can do this all on the fly without actually needing to know too much about it. We were able to sample this, get the right dynamics correctly in a nearly black box fashion. I wanted to tell you one other thing about this code. No, I'll probably remember later. Okay, so these are the conclusions of the part, and then I want to give you maybe 7 minutes left for part 2. The conclusions of this part are that derivative couplings are available in Q-Chem between excited states. Only, as far as I understand, they're only available between excited states, not between ground and excited state. At least I haven't put that code in. I'm not sure that's available yet. It would also be much less reliable as a practical matter. We can work at the CIS, TDHF, or TD-DFT levels. In other words, we can go beyond the Tam-Dankoff approximation. These derivative couplings are the key elements that tell you whether you should worry about electronic relaxation, and this can include any kind of electronic relaxation, but in particular, we're interested in electron energy transfer. If you want a rate of electronic relaxation, you can run short surface hopping, and again, this should be available very soon. Okay, as far as the second part of the talk, I just want to say a couple words about diabatic states here. And I think you've already heard, just 2 things here. In case you're interested about how you actually make a derivative coupling, well, I think I'll just skip this. The idea is basically you have to just take the full derivative of a matrix, of an eigenfunction as a function of position, and you have to worry about the excitations as well as the configurations. I'll skip how you actually do the work here. Okay, back to basics. As far as diabatic states go, if we go back to our earlier example, I told you that if you have a Hamiltonian, which is a very simple Hamiltonian like this, nobody knows exactly how to diagonalize this beast. Because if you diagonalize this part, you end up not diagonalizing this one. And if you want to diagonalize this one, you can't diagonalize this one. So we said that this failure to diagonalize the Hamiltonian was a feature of the Born-Oppenheimer approximation, and it really accounts for the fact that that electrons, that nuclei that there must be nuclear electronic relaxation, that electrons can relax and give energy off to nuclei. And we said that earlier that derivative couplings was a means of understanding electronic relaxation. Well, derivative couplings come about when you try to diagonalize this guy and not diagonalize this guy. Of course, there is the alternative option we just said, which is to say you can have the nuclear kinetic energy here and the potential energy here. This is already not diagonal. Why not just keep this basis? So why would you want to do that? Well, if this basis here actually had small elements in the off-diagonal, if somehow you knew that the off-diagonal elements were small, then you could use perturbation theory, right? This is basically what Marcus theory is. So could you think about doing that for these Clauss transfer systems? Well, in fact, you can. In this basis, by the way, in this basis of diabatic states, which is what we started with in reality for this model system I was trying to tell you about, you have the off-diagonals are called diabatic couplings, and the on-diagonals are called diabatic energies. And again, you would have to diagonalize this basis, this matrix if you wanted to get the adiabatic energies. What's the catch? So what if I wanted to work in a different basis? If I didn't want to use the adiabatic basis that I get from Q-Chem, I wanted to use the derivative I didn't want to use the derivative coupling, so I wanted to do something else. Was there a way for me to actually construct this other basis, this diabatic basis? And there are several ways of doing this. And Q-Chem actually, I believe, has more methods than any other program I'm aware of, because a lot of Q-Chem developers are actually interested in this problem. So, of course, the problem in general is that Q-Chem gives you the adiabats. You don't necessarily have 2 adiabats. You could have as many as you want. And you somehow want to rotate these adiabatic states that you get at any given nuclear configuration. You want to rotate them together and make diabatic states. And this rotation matrix should depend on geometry. Well, in this case, right, all you want to do really is sort of back out what this theta parameter is here that I told you before. So you want to find this theta parameter. Only now starting from the, and I'll skip this. So how do you do this? In practice, I know that in Q-Chem you have strain DFT localization, Boisseau-V localization, and ER localization. They can handle electron energy transfer, all the different variations you want, and they can handle arbitrarily many states, not just 2, which is a problem for a lot of other methods out there. Okay, so what does the Q-Chem input look like for diabatization? Here's the tip end of the molecule. I didn't have time to show you the whole molecule. This is for the Clauss system. Again, all you have to do, if you want to do ER localized diabatization, is you actually just need to say, I want to look with two states. I want to do ER, and I want to diabatize the first and second state. This is all publicly available now in Q-Chem. I'll skip the benzaldehyde and go right to the claw system. And okay, when you do this, there's one thing you want to check, right? Because you really want to sometimes do something else. If you've got good diabatic states, right, the whole idea is that in the adiabatic basis, you get these derivative couplings, which are the breakdown of the Born-Oppenheimer approximation. But for the diabatic states, they should have basically zero derivative couplings. They should just have diabatic couplings. And this can now also be checked explicitly in Q-Chem. So there's no more, there's how to put this? There is no more funny business. What am I trying to say? There is no more funny business in terms of having to sort of suppose that the derivative couplings are small. You can actually just check that they're small. And then you know that you really do have a totally other valid description of the electronic surfaces that you're working with. So you just say, I want to diabatize states 1 and 2, and I want to do derivative coupling between states 1 and 2. You can check this with Q-Chem, and if you do this, we did this with the Bois-OV method. What you can show is that the derivative couplings really are, over that full reaction coordinate before I told you, there's a huge peak in the derivative coupling when you go from donor to acceptor for the adiabats. But between the diabats, basically the derivative coupling is tiny, and this is almost certainly a numerical error. But it means in practice that you don't have to worry about it. But in general, you can always check to see how big they are. So let's suppose you do this. If you do this, I'm showing you now the same picture, and I apologize if you notice that this picture here is the inverse of this picture here. We somehow switched what was 1 and 0 or 0 and 1. What we're looking at here is as a function of going from the geometry where the excitation is on the donor to a geometry where the excitation is on the acceptor. What we find is that the whole way along there, as long as we actually do the diabatization gives us basically a constant diabatic coupling. And what's cool about that is that, and again, you can look at what the excitations look like, right? In the adiabatic basis, the excitations will be delocalized near the crossing point, but in the diabatic basis, the excitations will be localized. So if you look at this, the amazing thing is if you just look at what you get for that diabatic matrix that I told you, all you had to do was actually generate a 2x2 matrix to undiagonalize, yeah, your Hamiltonian. The off-diagonal matrix element, if you square it for that set of 4 molecules I showed you about, where I had the excitations on moving from the benzaldehyde to the naphthalene, experimentally, with the bond, you had 4, 5, 6, or 7 bonds in between them. Experimentally, if you look at the rate that you get, you look at its logarithm, basically it follows exactly just looking at the log of the diabatic coupling squared. So basically, you can, in the course of a half an hour calculation in Q-Chem, you can back out trends and diabatic couplings. These are also called electronic couplings, which give you strong, in this case, exact trends with respect to energy transfer rates for calculations that are very simple. Okay. And in fact, if I do show all 11 molecules in that series of the claw system, I get amazing agreement in general. Okay, so the conclusions from this part 2 are that you don't always have to do it the hard way, right? You don't always have to construct a derivative coupling. Sometimes you have to. If you don't want to, if you think that you're in the regime where derivative coupling may be not that useful, what you can always do for 0th order approximation is you can model electron energy transfer by making diabatic states and looking at the off-diagonal matrix elements that will tell you about the chance of transfer between 2 different diabatic states. These are now available in Q-Chem. In fact, not only is localized diabatization, but the derivative couplings of diabatic states are available in Q-Chem. Q-Chem allows you to verify that they have small derivative couplings, and then if you actually want to know the rate, not just what the couplings are, again, you know, we have this tendency in quantum chemistry to say, okay, I computed a matrix element, I'm done. What does it actually mean? Well, there is a lot of dynamics theory you can use that will actually tell you how to use that diabatic coupling and then get a rate out of it, something like Marcus or Redfield theory. Okay, so what are my final conclusions here from this talk? The basic functionality for analyzing electronic relaxation is now in Q-Chem as far as I'm concerned. You can do this analysis either in the adiabatic or the diabatic representation. If you're going to use the adiabatic representation, we now know how to make derivative couplings between excited states. If we want to use a diabatic representation, then we want to talk about diabatic couplings. And with both of these, all of these situations, you can actually talk entirely about not just, you know, electron energy transfer, but you can actually just say, oh, well, you know, my system had an electron which was actually in a Rydberg state, but then eventually the electron became localized in a valence state. How did that happen? If you want to get rates out, not just know that something's wrong, not just trends, you actually want to get real rates, okay? Then you really have to do something dynamical and go beyond the numbers I'm giving you here. So either you have to use surface hopping, which would then tell you how to do sort of Ab-Initio dynamics on the fly, which you can do in Q-Chem. Or if you want to work on the diabatic basis, you really need to use a rate expression that are sort of, and there are many of them out in the expression. You know, consult your local a dynamicist, but there's Marcus theory, there's the adiabatic version of Marcus theory, the non-adiabatic version of Marcus theory, there's Redfield theory. There are so many of these theories. You can build a model Hamiltonian pretty straightforwardly once you actually have these couplings that are available in Q-Chem. And what I've shown you is how things work for the Claus system and for benzaldehyde in detail. Okay, so let me just thank the people who did all the work here. The early work on diabatization was done by myself and some colleagues about 4 years ago. And in my group, all the work on derivative couplings was done basically by Shervin Fatahi, who's at Utah now, and Chi-U and Ethan Alguire. Brian Landry did all the surface hopping work, and I will thank you and take any questions you have. And I'm just about on time, right?
Yeah.
Okay.
So we have several minutes for questions.
And there's and maybe that went too quickly. I have no idea. I gave them a blanket fire.
So on your control panel, you should find a place for you to type the questions. So if you have any questions, please send them in now. We have one question from Isaac Tambling from Canada. What's the difference between energy transfer and electron transfer in experiments?
Okay, yeah. Okay. So in the original experiments that were done for these molecules, there were 2 experiments you could do. Okay. One experiment was one that I showed you about, which was triplet transfer. Let's see, should I try to go back, or how does it work? I mean, it's just easier to talk. You can go back?
Yeah.
Okay. All right. Wow, my machine is much faster than I thought it would be. Okay, so in this experiment here, right, what you have here is you have one electron over here going to move over here, and one electron over here going to move over here. So there's never a net dipole moment for the system. It's energy transfer in the sense that you have a triplet over here moving over to here. Now, what would an electron transfer be? So what these guys did was they actually took the ground state molecule here, and they came in with an electron. They photo attached an they sent in a low energy electron which attached into the pi star state, and then they watched that guy actually move over to here. So a very different beast between actually doing anionic charge transfer and neutral electron energy transfer or triplet energy transfer. Yeah.
Okay, we have another question about the manual. This is a question from Pradeep. Is there a manual entry on CIS derivative coupling and other related keywords?
In theory, that could be done today. So that's a very good question. I'll mark that down as something that has to happen. We have people. All of this code was done basically in the last 2 years, and it is all available now. And I know it's actually in the latest version of Q-Chem because we were in there, but I'm not sure we actually updated the manual. We will do that pronto. Thank you for the thought. If there are other keywords that you're interested in, please, when you look through the talk one more time, which is videotape, let me know that I missed them. We'll do our best to get all of them in there. Any that we know, why won't we put them in? We want you guys to have full access to all this, all of these codes. Yeah, go ahead.
Here is another question from Felix Placer from Heidelberg. How do you compute TD-DFT derivative couplings in Q-Chem? Is it just the same formalism as CIS? Does Q-Chem use the Casida scaling factors?
Okay, so the question that I'm being asked by Felix is about the following. TD-DFT, okay, so there are 2 different versions of TD-DFT, right? And I sort of gave us a hint of this, but I should go back and I should go look at the take-home slide because I actually say this here. Okay, so here, right? There are 2 different flavors of TD-DFT. You can work with TD-DFT either in the Tam-Denkoff approximation, which basically looks exactly like CIS. And so in this case, you want to do something which looks exactly like CIS. You sort of just want to look at you want to you want to think of them as having the exact same functional form, and there really is effectively a TDA wave function. Although you don't want to call it a wave function, you can just take the derivative of it, and you can see exactly how it does, and it has the right properties. And it has all the right properties around a conical intersection, which is what you're most curious about. If you want to work beyond the Tamm-Denkoff approximation, you have what's known that you have the full version of TD-DFT, which is the random phase approximation. And now you don't formally have a wave function. So there are two ways of doing this. Yeah, so we've worked on this, and I should say there's an article by Wenjin Liu actually recently who actually talked about this as well. So we've already published in these two articles here the formalisms that we've used directly here. And this is the work of my students Ethan Alguire and Chiu, where the way that they work with the full TD-DFT RPA is we define something called we define something called pseudo wave functions, which we can take their derivatives of and get and get derivative couplings. Now, what can I tell you about this approach? This approach is exactly equivalent to what Wenjin Liu calls the equation of motion, derivative couplings. There are many different ways you can arrive at the answer here, but the answer will agree exactly with response theory in the vicinity of a conical intersection. If you want the response theory exact answer, which will be slightly different, though we've been checking on it, and it's not exact, not very different, you'll have to wait maybe another month or two. That will also be checked in the Q-Chem as well, but that hasn't been published yet at all. We'll be working on submitting that in the next few weeks, I figure.
Just a follow-up question on that. Do you see any difference between TDA derivative coupling and TD-DFT derivative coupling in terms of the numerical value?
Well, the problem, of course, is that the numbers themselves can be totally different, right? Okay. So it's hard to sort of say how different are the gradients when the numbers themselves can be totally different, right? In other words, you find that sometimes when you're using TDA, where you think a conical intersection appears, actually it disappears when you have full RPA. So it's not so easy to tell you.
Okay. So one question from Michael Lecomte. Can you apply the diabatic method to a more exotic electron transfer process, such as triplet annihilation? Okay, so what you are asking me, I believe, is can I actually couple things to the ground state? This is a very interesting question. How do you diabatize and actually get things to go to the ground state? Certain cases you will be able to, certain cases you will not be. I have to think about triplet X. Let's just see for a second here. In theory, okay, so the theory, I'll put it this way. The theory, I'm sure, would work. The question really is how do you actually generate the adiabatic states? The method itself is completely general, right? Using sort of Boy's localization or ER, I didn't tell you what these things were. These localization methods are all designed to try to maximize charge separation, or which comes about from assuming from a given model of a solvent, or trying to maximize charge solvation, which comes around also from different solvent models. These methods, the methods that we have for diabatization, are very well grounded in theory, so they'll work. Now the question is, do we have electronic structure packages that can reliably give you in a balanced manner the ground state in conjunction with excited states which represent triplet states? And in this case, you'd have to do something like a double spin flip calculation, it seems to me, something along the lines of what people have looked at for singlet fission. I presume that that's possible. I don't know why nobody's done that, but that would be something that we actually could do pretty easily if you believe the energies you get out from the double spin flip calculations. That's the whole point. So it comes down to really the basics of the electronic structure, not just the diabatization method. Something to look into, and I'll certainly I'll see what we can say here. And if you're interested in this, please let me know. I'll be happy to work with you. Okay, here's another question from Christian. Are there theoretical or practical Q-Chem limitations that would create problems for examining inorganic complexes?
So the big question for inorganic complexes, right, is going to be how you deal with the multitude of excited states that you're going to have here. So we've been working on some pet projects of our own, which I hope will actually come to fruition very soon for treating this. If you believe that TD-DFT can give you reliable excitation energies, forget about looking now at an energy transfer. Do you actually believe the absorption spectrum you get, all right, from a TD-DFT calculation? Do you're going to shine UV on your inorganic system. It could be organometallic. If you believe that TD-DFT actually gets that for you correctly, then there's no problem. Everything I've told you about works great for inorganic complexes. The question really is going to be, do you believe that TD-DFT works for those systems? And from what I hear, sometimes yes, sometimes no, right? Open shell singlets are going to be a real pain. So on the other hand, it's sort of remarkable how well my colleague here, Eric Shelter, has told me that some of the times for some of the F element stuff that he's working on, which I would expect it to give a very hard time, it works great. So it's a little bit hard to know in practice. It will depend. It's got to depend basically on how close your inorganic complex looks like a simple mean field solution, which really means how close it is to anything, at least in the ground state, which is closed shell. So ruthenium, probably it's going to work much better than, I don't know, nickel. That would be my guess, but I wouldn't hold me to that. But what I would tell you is, if you believe the electronic absorption spectrum, if you have the right functional that works best for the electronic absorption spectrum, then all of this will work there, no problem. And if you're curious, contact me. I can walk you through this with as much detail as you like. Yeah.
Okay. Here another question from Xiaolin Dan from Colorado. In the output file for large systems, only less than percentages of the real CIS wave function is showed. Is there a way to get more than 90% of the real CIS wave function?
This isn't exactly my expertise. I mean, the whole CIS wave function is, of course, there. It's just sitting there. I don't know. Is there a rem variable that allows you to actually print out the wave function?
Yeah, the default value is 0.15, namely that if the amplitude is larger than 0.15, we'll print it. Otherwise, we'll not. But there's a keyword. Probably CIS amplitude print, something like that. It should be in our manual.
Okay. So
you can, if you set it to 0.1 or 0.05, you get more amplitudes print out. And here is another question from Pradeep about conical intersections. How to define a circle in the n-dimensional space? It seems that you should be able to draw many circles around a canonical intersection, and doesn't matter which one you use.
Well, so this is the beauty of it. Okay, so I was a little bit loosey-goosey with what you would do here. First of all, if you're, right, there's a really the whole notion of which circle you draw around the conical intersection has been very well shown by Berry. This whole question of Berry's phase about a circle that encompasses a conical intersection, that will not depend at all on which circle you have. Either it encompasses the conical intersection or it does not. The phase difference that I told you about, that's enough to prove or disprove the existence of a conical intersection. You're saying, maybe what you're asking though is, in practice, how did we actually get this? So we found a point very close by, and then there are many ways you can do this, but the simplest thing to do is just literally to do a whole bunch of calculations right around there. If you convince yourself that the derivative couplings always lie in one plane, then just pick whatever point you started with and just walk in that plane around that point. That would be the simplest thing to do. But there are many. You don't have to be that particular. The nice thing about these circles that encompass regions of conical intersection and that tell you that there is one here through a Berry's phase, through a circulation of the derivative coupling, is that it's very robust to which circle you chose. So you don't have to be too careful. That's the nice part. It also works for remarkably big or small circles. You'll find that it works for circles of, even in practice, right? In theory it has to, but even in practice it works for circles, anywhere from as big as 0.2, 0.3 angstroms oftentimes before it breaks. Yarkoni has talked a lot in the past about how robust this approach is for actually calculating conical for verifying conical intersections.
This concludes our webinar. We would like to thank Dr. Joseph Diabatic for his excellent presentation. If you've not tried Q-Chem lately, we've come a long way, and we invite you to utilize our 2-month full-featured demo, which you can request by hitting the orange free demo button on our website. Should you have any questions, please feel free to contact us by emailing either Jinting or Yihan at the email addresses noted on your screen. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.